5 past, so I'd like to make a start. This is a continuation. I started this lecture partly because it's quite a difficult one, so I kind of forced the pace with lecture 24 on the Faraday's law, which was relatively easy, just a crossbar moving backwards and forwards. The idea of the field energy, of course, we've introduced that we've got the electric field energy is epsilon naught over 2 E dot E, and the magnetic field energy epsilon naught C squared over times B dot B. So this is fundamentally the energy density in all circumstances in the electromagnetic field. So this is a completely general formula which of course, it contains static cases, but it also includes electrodynamics. So I then went on to say, well, the negative rate of change of the energy density integrated over some volume. Obviously, if I integrate the energy density over a volume, I get the energy within that volume. Well, the negative rate of change of that has got to be equal to the outward flow, and the energy flow vector is this capital S, Poynting's vector. And because of the unusual coincidence that the capital S is Poynting's vector, I've called this an area integral. I've usually called it a surface integral. And I was pointing out last time that without this term, it's incredibly similar to what we did with charge conservation, except here we had a rho, and so this integral became the total charge. This was J, this was the current density vector, and integrated over the area was carrying all of the charge out of the volume. But with the electromagnetic field, there's obviously also the possibility of the energy being converted into light, heat, and so on. And I'll come much more to this in the lecture or sort of problem class that we're doing at 11, is why this is the correct term for the work done on matter within the same volume. And then again, a kind of trick that we've used throughout the course, I was able, with Gauss's theorem, to transform this surface integral into the divergence, the volume integral of the divergence. And then again, I've got 3 volume integrals equal to each other, so the integrands have got to be equal. And again, I hope you recognise that without this term, this would be like our differential expression for conservation of charge. Minus d rho by dt is the divergence of the current density, which is a very important result when we were deriving the Ampere-Maxwell law. Now, without proof, I went on to give the Poynting vector as equal to epsilon naught c squared E cross B. And as I say, this can be derived from the Maxwell equations. It's a little bit of a long proof, and the book that I'd recommend for that, if you really want to see this derived from first principles with the correct mathematical derivation, the Panofsky and Phillips is a very good book for that. So those 4 equations are going to form the first 4 equations of the lecture, and I'll number the equations as we go along, 25, 5 and so on, these being the first 4 equations of the lecture. So having covered that general idea of field energy and Poynting's vector, I just introduced last time very briefly, again of course these should be vector symbols, this was copied from a book, so this is the Poynting vector, the electric and the magnetic field vector. And of course, it's exactly what we would expect. Now that we've done Poynting's theory, we kind of can look at this the other way round, that if we have an electric field vector perpendicular to a magnetic field vector, as we know we do in an electromagnetic wave from the fundamental solution of Maxwell's equations back in lecture 11, then the direction of propagation of energy flow in the field is perpendicular to both. That's precisely what E cross B is telling us. And of course, this will be the direction of wave propagation. So in a sense, we haven't at this stage learnt anything new. But we'll see in this lecture that Poynting's vector throws up some rather unexpected results in different circumstances. But in this circumstance, it's obvious from what we knew already. Though, of course, having the constant in the equation is a very powerful step forward. So equation 25(4), in other words, this, again, as I say, I'm going to use for all the equations, these four will be the first four. So when I refer back to them, this the 25(4) is the fundamental equation for Poynting's vector. Then, so equation 25(4) for the energy flow vector, that's S. And again, just to emphasise, this is in joules per square metre per second. This vector is telling us how much energy is flowing per square metre per second in the field. Is easy to apply to EM waves and doesn't give us anything new. And this is illustrated in figure 102 of the course handout. Again, of course, with this new formula for the energy flow vector, we'd be very worried if it didn't point along the direction of the flow propagation. So we already know that. But now we're going to apply some of the results that we used when that we derived from the field. And again, I hope you remember that since B is equal to E over C for an EM wave in a vacuum. And again, I'm not going to go into materials at all. We're going to continue to do what, if you like, Maxwell's equations in free space. We're going to continue to look for the vacuum, that we can write that the magnitude of E cross B is equal to, well, it's equal to, we've got the general, again, I'll just scribble on the bottom here that in general we've got that S is equal to epsilon naught C squared E cross B. And as in an electromagnetic wave, these are at right angles to each other. The magnitude of E cross B is just E times B because there's 90 degrees between them. So the magnitude of this is just EB. Well, it's more usual, rather than write epsilon naught squared EB, to use the fact that for the light wave, as we've already proved, the magnitude of the electric field is C times B, and the usual thing is to eliminate the B here. So to write the B here as E over C, and then obviously I've got a cancellation here between the C squared and the C. I get epsilon naught C E squared. And please be careful with this formula. You get so used to seeing C squared. C so often comes up in formulae in electromagnetism as C squared that it's very often people are tempted to put here the magnitude of the flow as epsilon naught C squared E squared. It isn't. We've got the EB, and we use the fact that B is equal to E over C, and that gives us epsilon naught C E squared for so I'll write that explicitly, that this is equal to E squared over C, which is equal, which gives us that the magnitude of the Poynting vector is epsilon naught C, and that is the correct C, not C squared, and this is equation 25(5). So now, you remember, like throughout, this is indeed what we would call the irradiance of a wave. So, just to go across here, the average, we'll have to be a bit careful. I'll explain the importance of the word average in this in a moment. The average rate of energy flow is called, of course, the intensity or the irradiance of the light. So when we did optics, we just wrote some arbitrary amplitude for the electric field vector, and we said, well, we don't know yet the constant that is going to relate that to an absolute intensity, now we have that constant, we have that the intensity of light, or of course electromagnetic waves in general, is the average value of the Poynting vector, which is epsilon naught c times the average value of E squared. So let's make that equation 25(6). So the constant that actually relates the irradiance to the square of the electric field is epsilon naught c. So again, comes out in terms of these fundamental constants. So the next thing is to be aware, of course, in an electromagnetic wave, the electric field is varying from place to place. And so we do have to just be a little bit careful with taking an average. I mean, obviously, here's a sketch. It's just not one of the course sketches, but it's taken from any old book. That, of course, in a real electromagnetic wave, if this is, say, the direction of propagation, and as we're in a vacuum, this must be, of course, exactly the speed of light in a vacuum, 3 × 10⁸ meters a second, well, the electric field vector is varying in space. So, of course, if we take E dot E here, we get a different result to here, and to here, and so on. But as we know, if we go over an entire period of oscillation of the wave, so if we follow back through an entire period of oscillation, basically the electric field over a period is just a sinusoidal variation. So the average value of E squared is, if you like, E naught squared, where E naught is the amplitude here, times the average of something that is varying sinusoidally. And it doesn't matter what we've got in here, it's a sinusoidally varying function, and so if I average any sinusoidally varying function over a period, well, the average value, of course, if I square this function, the cosine, a sine function, I've drawn it as a sine here, but obviously we can shift the origin along, the average value over a period, of course, is a half. So the average value of E squared in an electromagnetic wave is equal to a half E naught squared. And that just means that exactly we spatially averaged the energy, and over a complete period of the wave, the average of E squared is equal to a half times the amplitude E naught squared. So we just have to be a little bit careful with the averaging there. Now, what I would like to show too is that this, I mean, again, we've not proved Poynting's vector from first principles, but I'd like to show that this is equal. I'll just make a quick note on that first of all. So the average of E squared is a half E naught squared, where E naught is the amplitude. So we'll just need that note in a moment. So I think that's relatively straight. I mean, it's the same reason too. When we have AC mains, I mean, like a light wave will be oscillating at, say, 5 × 10⁻14 hertz, and we've only got to average over a very short distance, the wavelength of light, in order to get this average energy being carried by the wave in terms of its amplitude. But if you want to excuse me, at least see that this is compatible with our energy density calculation, and we did do that fairly rigorously, that follows quite straightforwardly. And again, it uses ideas, there's a lot of this work on energy density that is very, very similar to the ideas that we used in charge density. And again, I'm going to use that charge density view graph to illustrate the point. So let's just move on to that. So, I mean, that's almost a trivial point, that we've just got to average the energy over a period. Clearly, E is varying from point to point in space, so he has to average it. Now, we looked at this before that if I've got, in this case, I had a charge density rho, just representing some blob of charge that was moving along with some velocity v, and we could see almost, you can imagine, just take any infinitesimal area within the blob and apply dimensional analysis to this sort of box of charge, how far it's moved, that I get the current density vector J. And so we used this important relationship when we were working with the ideas of charge conservation. And again, this one, rho was in coulombs per cubic metre, the velocity, of course, in metres per second, and then we got this flow vector. Now, likewise, we could imagine this to be a blob of energy density lowercase u. It's certainly travelling at the speed of light. Wouldn't be a photon, wouldn't be an electromagnetic wave unless this velocity was c, and the equivalent case here to the current density vector is the Poynting vector j. So in terms of magnitudes, we'd have that u, again here replacing this equation, we'd have u replaces rho, c is of course the velocity in this case is the velocity of light, and this, of course, is in joules per cubic metre, and this is in joules per square metre per second. This is equal to the magnitude of the Poynting vector. So, in other words, you've got, if we got the energy density in the field and we know it's travelling at c, our expression for the Poynting vector should be u times c. So let's follow that through. Let's show so that the equation 25(6), this is the equation that I've left up on that board, is compatible with equation 25(1). And again, remember, equation 25(1) is just that the energy density is a half E squared, epsilon naught over E squared plus epsilon naught C squared over a half B squared. So for an EM wave in a vacuum, again I should stress this only applies to a vacuum. We know from our work on refractive indices that light's going to slow down in another mediums, but let's just stick with the vacuum so that we can use our C. The energy density is equal to epsilon naught E squared over 2 plus epsilon naught C squared over 2, and now B squared is E squared over C squared. Again, for an EM wave, is only true for an EM wave in a vacuum. Don't make this manipulation in other circumstances, but for an EM wave in a vacuum, the electric field vector is C times the magnetic field vector. So when we put that in, the B squared becomes E squared over C squared, and you can see it's a very beautiful formula because the C squareds cancel, and we've got epsilon naught E squared over 2 plus epsilon naught E squared over 2. So in other words, in an electromagnetic wave, the electric and magnetic field vectors are carrying identical energy. So it's only in this particular case, I should stress, where E is CB, we can substitute here for our B squared, the E squared over C squared, the C squareds cancel, and we're left with these two equal terms. And of course, if I add up a half epsilon naught E squared over 2 with the half times the same thing, I get this very beautiful, simple result is equal to epsilon naught E squared. So this is a very lovely, clean formula. And like I said, a lot of the time when we looked at EM waves, I said we're only going to concentrate on the electric field vector because that's the one that interacts most with matter. But you can't neglect the magnetic field vector. As you can see, the magnetic field of an EM wave is carrying an identical amount of energy. And the two add up to give this incredibly beautiful, simple formula. But now, we can almost say by dimensional analysis and C fig 43 for the analogy with charge density. So again, this is a result we used earlier in the course, that the charge density times the velocity is equal to the current density in terms of magnitude. Well, we've got the U times C is equal to S. So we have, by dimensional analysis, S, the magnitude of the Poynting vector for an EM wave, is U times C. And again, you can see this is clearly going to work dimensionally. This is in joules per square metre per second. This is in joules per cubic metre. And this is in metres per second. But now we've got the energy density of an EM wave is at epsilon E squared. We get that the magnitude of S is C times that, which is epsilon naught C E squared. And of course, that's the same as this formula. And remember, this formula came directly from taking that the Poynting vector is epsilon naught C squared E cross B. That gave us this formula directly, but we can also, by this kind of argument, say, well, if we know the energy density for an EM wave, we can certainly calculate the Poynting vector by that method. And of course, it's physics, it's beautiful, the results are in perfect agreement. We get epsilon naught C. So I'll just now mention the averaging, because this one, normally, when you consider the irradiance, you're of course considering the average of the energy being carried by the wave. So we can also write equation 25(6) as the average of the Poynting vector. Well, we know it's epsilon naught C times the average of E squared, and we know the average of that is a half E naught squared, so you'll often see it written as a half epsilon naught C E naught squared. So this, let's make this 25(7). And so again, we've now got this form, with the factor half from the averaging, this is truly now the irradiance of a light wave. It's the average value of the energy flow vector, and it's epsilon naught times C times a half times the square of the electric field. So if you like, we've now recovered the optics from a completely different angle, and we've come up with this formula. So there we go, we're about halfway, and you might think, well, okay, that's nice, we've got this constant, but we haven't discovered anything new really from the Poynting vector apart from this one constant. What we, however, will get into, we're going to do this in detail in the problem class, this charging capacitor. And now things, and I have to be honest with you, they start to get a bit weird, and they'll get weirder in the next half hour. Because the point, you think, yeah, the Poynting vector, that's intuitively obvious. EM wave, waves going that way, electric field, say, this way, magnetic field this way. The energy, of course, is going with the wavefront. But when you're charging a capacitor, where is the energy coming from? And your first intuition, or my first intuition, is, well, it's coming down the wires. You know, you're putting electrons down wires, you're piling up charge on a plate, and you would somehow think that energy is flowing down the wires. And you'd be completely wrong, because it's not. If you think about this situation carefully, we've got the current is flowing down, let's say here, we just consider conventional current. We've got a current flowing in towards the plates. Well, we know, we did the calculation by the Ampere-Maxwell law, that, of course, the changing electric field between the plates produces a magnetic field that circulates. It's like the field of a current carrying wire. So if the wire is in this sense, the magnetic field is going round in circles. So we did this from the Ampere-Maxwell law, and of course we know the direction. If the current's this way, right-hand screw rule, the magnetic field is exactly as shown in this sense here. It's turning, the magnetic field lines are circulating around the capacitor. But then equally obviously, we know that inside the capacitor, well, there's a load of negative charge piled up on this plate, a load of positive charge piled up on this plate. Obviously, the electric field lines are pointing from the positive to the negative plate. And we've used that a lot. So there's my electric field. There is my magnetic field. So let's say at this point, coming round here, it's pointing towards you there. Well, what's at right angles to both of those? That's clearly pointing in this direction, which is in towards the centre of the capacitor. So when you're charging a capacitor, the energy flow vector is directed radially inwards. So, and remember, this works completely if the capacitor is in a vacuum. So when we send current down a wire onto a capacitor, the energy flows in through the sides of the capacitor from the vacuum, flows in from space-time. It emphatically does not flow down the wire. So as I say, the Poynting vector, it seems kind of obvious in an electromagnetic wave. Of course it points along the flow of the wave, but when you're charging a capacitor, the correct analysis gives you the electric field in this sense, the magnetic field in this sense, and so wherever you are as you go round, what is at right angles to the tangent and the normal along the wire axis is radially inward towards the centre. So there's the first of our slightly surprising results. So, and I think because it's so counterintuitive, it's probably even worth saying, although its application to light waves seems obvious, I mean, getting the exact value of the constant wasn't obvious, but the direction was obvious. So although that seems a kind of obvious application, the Poynting vector can be counterintuitive in other cases. I'm just psyching you up gradually for the really weird one at the end of the lecture. But I think this is already rather counterintuitive, that when you're charging a capacitor, you get the energy flow vector coming in from space-time. And I mean a vacuum, the energy is flowing in from the vacuum. It is not an immediately obvious result. So it is, however, true, and we'll see. I'll go through the derivation in detail. For example, suppose we are charging a parallel plate capacitor. So, again, this is a very, very prosaic circumstance. It's not like we're choosing some kind of weird physical situation. I mean, we just connect a capacitor to a battery, and that's extremely straightforward. And this is illustrated in figure 103 of the course handout. Well, the total, again, we'll use this in more detail later on. The total energy between the plates is, well, we know, we've worked this out, we've got our epsilon naught E squared over 2, that's the energy density, times pi A squared H. And again, I'll use this in the talk at 11. I'm going to have a circular capacitor with plates of area A and the separation, you can think of h for height if you like, h. So we know that the energy density of the electric field inside the capacitor is given in this way. So I think we're up to equation, 25.8. So du by dt, again, this is, I'll write it, perhaps it's a simple chain, the level of maths you're at, it's a very simple chain rule application. It's du by dt, dE by dt, which is equal to epsilon naught pi a squared h e dE by dt. Clearly, if I differentiate u with respect to e, I just bring down this factor, this becomes epsilon, the 2's cancel and I just get epsilon naught e times the pi squared a h dE by dt. So there's got to be a flow of energy in from somewhere, because we know that as the capacitor plate, again, it's absolutely straightforward. We know the electric field in a capacitor is just the surface charge density on the plates over epsilon naught. So we know that if the field's decreasing as a function of time, or increasing if we're charging the capacitor up, then necessarily du by dt is changing. Of course, the energy in the capacitor is changing as a function of time. But it's not obvious, I think, that... Hang on. It's great lecture theatre for blackboards, this one. Let's have another go. Last one, I think. The last one I'll just do as sort of qualitative notes, maybe. So we've got the... there must be a flow of energy in from somewhere. Obviously, if the energy between the capacitor plates is changing as a function of time, it's got to flow in from somewhere, but not, emphatically not, from down the wires. It comes in from around the edges. And the detailed maths we're going to do, the maths works fine, and we'll prove exactly, quantitatively, what happens when we discharge a capacitor later, and that one, I'll call it problem class B. We had one problem, whole cohort problem class earlier in the term. So we've got already a slightly strange situation where energy flows in from outside the capacitor. So also, by the same argument, the same thing happens for a wire, and that's what's illustrated in figure 104 of the course handout. Prepare one last blackboard just for a quick note on that. But if you've got the hang of that situation, then I should say too that there is a kind of qualitative way of thinking about it. Imagine we start off with a charge here and a charge here. This is, I should emphasise, is very qualitative, but just to give you the feeling of why the energy may behave in the way it does. Well, again, we're going to do this field in more detail next term. It's called the electric dipole field. But, you know, you've already done that kind of thing in EM1. You've got two static charges. We know how to calculate the field and draw the field lines. Well, if you like, when the charges are a long way apart from each other, the field lines look like that. But when they've been piled up on the capacitor plates, the field lines have all got bunched in the middle here. So you could think qualitatively what's happening. This is a very qualitative hand-waving way. We're going to do the proper maths later on, is that the field lines have kind of been sucked in towards the capacitor plates. That as the charges pile up on the capacitor plates, the electric field, which has been very diffuse, is now getting concentrated in between the capacitor plates. So you can sort of get the feeling that it's quite reasonable, actually, that while we're charging these plates up, the energy is coming in this way, because we know the energy is going to be proportional to the square of the electric field, and we know that the electric field is getting concentrated as we bring the charge up onto the plate. So it's not such an unreasonable result when you think it through. It's just a bit surprising at first. And of course, it's, you know, it's physics, so it's a true equation. Now, what is perhaps again a necessary follow-up? And again, this doesn't look to you probably exactly like Ohm's law. I'll come back to that later. Again in the following problem class, but this is a statement of Ohm's law. You know, you're more used, of course, to writing it as V as IR, but come to that later. This is, if you like, a more sophisticated way of stating Ohm's law. And again, all it's saying is that an electric field produces a current density in the same direction. So in other words, in order to drive a current along a wire, well, one obvious way we could do it would be to connect it to a battery. And of course, that produces an electric field, and it's the electric field that drives the electrons. So saying that the current density is proportional to the electric field is fairly obvious. But again, in this case, in order for the current to be driven along the wire, the electric field has to be along the wire. And we have done it to death so many times. Of course, we've done the field around a current carrying wire. It's tangential. So the field is tangential. So again, it's the identical geometry to the geometry with Poynting's vector for the charging capacitor, is that my S is radially inwards towards the wire. So when next winter you're freezing and, you know, students, you've just got one single wire to warm your hands by, and you pass the current along, and there you are, you're warming your hands by the wire, at least you can say to the non-physicists who you're living with, says, yeah, well, you can at least say, well, the thing that's keeping us alive in this room is energy flowing into that wire from the vacuum around it. Anyway, it won't make you very popular with your housemates, but at least it will be true. So, similarly, for a current carrying wire, the Poynting vector is radially inwards. So again, energy is emphatically not flowing down the wire to heat it up or make it glow if it's tungsten and we want to make a light bulb. It's being drawn in from the space-time around the wire. And that's illustrated in figure 104. And here we go, we've got a few minutes for it. The really weird case is illustrated in figure 105. I think even the case in figure 104 seems reasonable enough once you've got the idea of perhaps the field lines being drawn inwards in the capacitor, you know, so then you think, well, okay, let's think about a wire in the same way, and again the Poynting vector, if you like, as we pass the current along the wire and it heats up, the energy is coming in from the surrounding space-time radially. But the next case is extremely weird. And the next case is one that made people doubt the Poynting vector theory completely. I've got a demonstration experiment for this one. God, this is a moment of pure excitement. Shook the audience. So, here we go. Let's clear a bit of space here, if I can. If you've got a static charge next to a static magnet, that's the case that's being illustrated. So I forgot to go into the labs to collect my bar magnet yesterday, so use your imagination, bar magnet, yeah? Also, this is very large for a point charge, but it's going to represent a point charge. And I'm just now going to put a static point charge next to a static bar magnet. That is obviously a completely static situation. There they are. But now let's consider the field lines from the bar magnet. Well, we know, let's imagine this is the North Pole, this is the South Pole. The field lines are going to go like this, and as they reach the equatorial plane, they'll point downwards into the plane. Yeah? So likewise, of course, that doesn't matter. The field lines, there's the North Pole, they'll go round, they'll go downwards into the plane here. Of course, they'll come back up and join the South Pole here. Likewise, they'll go downwards. So in this equatorial plane, the magnetic field in the plane of the table is always pointing vertically downwards. We know the field of a bar magnet, we know the field of a solenoid, we've proved that. But now we know also that the electric field, so there's the magnet producing its field lines which are going down into this plane, and there's a couple of them, for example. We now have a static point charge, and we know that from a point charge, all the lines are just going to simply radiate outwards. We know that a point charge is a source of a field that just produces a spherically symmetric charge distribution. So let's have a look over here. The electric field's pointing this way, the magnetic field is pointing this way, so the vector that is at right angles to both of them points this way. It's emphatically a non-zero pointing vector, and it is pointing at this point directly towards you. Likewise, here, there's my electric field, yeah? My magnetic field is still vertical. At right angles to both of those, here, the pointing vector is now pointing across the lab, the lecture theatre in this way. Similarly, and of course it follows, here's my electric field, my magnetic field's vertically downwards. At right angles to both of them, the pointing vector's now this way. I keep following it round. Here's my radial electric field, here's my magnetic field. At right angles to them both, the pointing vector is now this way. So in other words, the pointing vector is going around in a loop. So this is the slightly strange situation, is that we've got a static bar magnet and a static charge, but we have got a pointing vector that is flowing round in circles. So there appears to be a circulation of energy in the electromagnetic field in an entirely static situation. So there appears to be a circulation of S in this purely static situation. However, being as it follows from the Maxwell equations, it must really be there. A lot of people don't think it is there, but let me now finally come back. Do you remember a paradox from earlier in the term? Something about a charge ball, rotating charge balls in a sphere. Because if you remember, the nature of the paradox here was that we somehow interrupted, which we could have done without touching the system. This, remember, could have been a superconductor, and we might just have let it warm up, and then the current decays, or the battery lead might have fallen off. But we got a di by dt, and that gave us a dB by dt. And then by Faraday's law, that gave us an EMF, which was the negative rate of change. And that EMF would appear to have interacted. Remember, it's a circulating, it's an abbreviation for a non-zero line integral of the electric field going around, and that non-zero circulating electric field should act on these charges and make the disk spin. And the answer to the paradox is very straightforward. Yes, the disk does spin, and the reason is that the electromagnetic field possesses angular momentum, and that angular momentum is given up to the mechanical system. The angular momentum of the universe is definitely maintained, but this, if you like, you can see just from this example, this strange static case here, if you've got a circulation of energy, if the energy is flowing around in circles, you've certainly got angular momentum. And so we haven't got the time in this course to go deeply into it, but we've just done field energy. The electromagnetic field quite definitely also possesses momentum and angular momentum. So we'll just wait until it steadies down here. You agree that that's not moving at the moment? It's sort of wobbling a bit, you know, because we're in the floor in Vanbrugh. Feel like a minor earthquake every time I move up here, and I disappear down a crevasse. But you know, this is a classic example. I mean, basically, it's a sort of photon windmill that you've got white sides and black sides to the sails. And again, just considering, let's say, if we've got a black side to the sail and a photon hits it normally, well, the momentum of the photon is just absorbed, so the momentum change is p. If we've got a white side, well, the momentum change is 2p because the photon is actually reflected. So it was a bit unfortunate we didn't have a chance to look at absorption and re-reflection of radiation. I missed out that, you know, why are metals shiny? But in that system, there's a vacuum inside there. There's absolutely no mechanical motion, and this is the same effect, that even with something as weak as a bike light, I can make this thing rotate. Now, it's perfectly clear, I mean, it's a very weak effect, but the electromagnetic field is giving momentum to a mechanical system and making it turn. So that is basically, although this theory seems very odd and seems to give these strange counterintuitive results, like circulation of energy in a completely static situation, it brings up the idea. And you know, you can read about this more in advanced texts of momentum also in the electromagnetic field. But the field itself is physically real. It's got energy, it's got momentum, it's got angular momentum. It's not just some like calculating device. Anyway, that sort of finishes the main bit. Let me just say, however, it's been a long term. Congratulations for turning up on a early morning. I just want to say I'll follow this up a bit more later. You don't need to sort of particularly take notes on this because I'm going to email people about it as well. But it is, of course, a big course. No, you probably noticed. I certainly feel it towards the end of the term. And I'm not going, to help you with your revision, what I'm going to do is not tell you, of course, what's on the exam, but I'm certainly going to tell you what's not on it so that you don't have to, you know, waste time. And the exam is around, of course, we're going to have something on Ampere's law, something on Faraday's law, something on the Ampere-Maxwell law. I mean, these are 3 of the 4 Maxwell equations, and I'm assuming you've covered enough of Kieran's course on electrostatics. Obviously, then we have EM waves, including their reflection, refraction, and polarization, and we've got diffraction. So you can see that's obviously 5 topics, and then likewise, of course, there's the general form of the Maxwell equations, the energy topic that we've been covering in bits in the last week or so. So what I'm not going to examine, although it's a shame here, I'll give one of these lectures maybe after the exams because I think some of you quite enjoy them. I'll leave out the field tensor one and do relativity on Friday by saying that that's not on the exam. I'll probably now be talking to an empty lecture theatre on Friday, but that's life. Obviously not why are metals shiny because we didn't do the lecture at all. I'm not going to say, I mean, when I say cross out the Cornell, you do need to know that near-field interference exists, but you won't be asked to do any calculations of that. You will be asked to do calculations of far-field diffraction, things like, you know, Young slits and, you know, single slits and so on. That's definitely on the syllabus, but not the Cornu spiral. Likewise, dipole radiation is quite a difficult topic, which I sort of like gave very briefly in order to bridge the topics of the speed of light to the optics part of the course. And similarly, although it's important conceptually, anything that I set on the steady magnetism in the exam, you won't need to use the vector potential. It will be solvable directly from Ampere's law or the Biot-Savart law. So And I should say too, I have covered 5 of the 6 questions on the exam that you'll get next term. I'm going to set 1 question on electric and or magnetic materials and 5 questions on this part of the course. And as I say, basically eliminating, of course, I'm not going to give that lecture. That one is not an exam topic. So at least it takes out 1, 2, 3, 4, 5, 6 of the lectures are basically not on the exam. So, you know, the exam's going to concentrate on the fundamentals, the Maxwell equations, and these ones are the ones that we concentrated on. There's the EM waves and the diffraction. These are the main topics. So I'll see you in about an hour's time. Have a nice